Good afternoon, everyone. Welcome. Let's get started. So let's look into the future a little bit. Your draft version of Part 2 is due on Tuesday, the 1st, by 5 o'clock. Originally when I'd picked that deadline, we were going to have classes on Tuesday, but they switched things around. I decided rather than bringing that deadline forward, I'd just leave it where it was. So I guess you'll have your first day of vacation that you can work on this if you choose to waste your vacation time on your classwork. If not, you can just submit it early and then start having fun. Homework 12 is due a week from today. We're going to go over some more air quality things today. I've just handed out a copy of that assignment. It's also posted on iLearn if you need a PDF copy of it. Any questions related to the announcements? Okay. Well, let's continue talking about air quality. Last time we were talking about the effect that if the sun is heating pavement all day long, when the sun goes down and the air starts to cool, then that can cause a temporary inversion above a city at night. Why is an inversion a problem? Anybody remember what's the big deal with an inversion? That's right. Yeah, an inversion is when the pollution is trapped. And so we really want to avoid inversions or avoid being in a polluted area during an inversion because it's keeping all of the contamination that we'd experience close to where the humans are. So a heat island is that effect of an evening time inversion. Another way that air pollution can be moved around from place to place is the daily effect of when you're living on a coastal area, the water and the land heats up at a different speed. And so during the daytime, the land gets heated up, but at night, you can see the moon is up, that's how we know it's night, the water is warmer than the land. And so the air is rising above the warm water, and it's cooling above the cooler soil. And so that causes sort of a breeze that's going out towards the ocean in the evening time. But during the day, it's the opposite effect. During the day, the soil heats more quickly than the water does, and so the air will be rising over the land and falling over the water, and so it's bringing the air from the sea during the daytime hours. Now, of course, there's exceptions to these. If there's a low front somewhere or a high-pressure zone, then that could alter whether it's a land breeze or a sea breeze, but these are sort of the typical patterns that can account for the movement of air and the movement of air pollution on a daily cycle basis. Why is air pollution bad? Well, not only does it hurt people, but it also hurts property. The air particles that can settle onto buildings can have a corrosive effect on the things that buildings are made out of. All through Europe, if you go through some of the downtown areas, especially in the former Eastern Bloc countries, the cathedrals are sometimes very heavily stained by soot and particulate matter that's landed onto buildings. And sometimes, depending on what the air pollution is, if it has an acidic characteristic, then it can eat away at things even like limestone, which is sometimes used for old and important buildings. So here are some of the mechanisms of deterioration. Here, in the UAE, one of the concerns that we have is that there can be a lot of dust particles in the air when it's very windy. And so that's not a man-made air pollutant, that's a naturally occurring air pollutant, just dust particles and the abrasive effect that can have on buildings or vehicles. Sometimes, though, when the air pollution is settling onto a building and it has to be cleaned off, it's just the process of scrubbing and the cleaning effects that can cause a deterioration of the materials. Yeah. Yeah. Lasers? Yeah. Yeah, I guess, the laser can heat and burn away some of the oxidation, and probably that gives them more control than if they're going to be rubbing it with a cleaner, if they want to avoid using something that will do chemical attack. Now, direct chemical attack is if you have acid rain that falls onto a limestone building, it's going to dissolve the limestone. But indirect chemical attack is when the pollutant goes into the material, and as it seeps through the building material, then over time it's a more lengthy breakdown process. And electrochemical corrosion is just when two metals that have a different oxidation state touch each other. One of them is going to go through an anode reaction and the other is going to go through a cathode reaction, and that's having to do with any two dissimilar metals. The electrons will pass from one to the other and can cause a corrosive effect. And so if there is like even just steel particles, very fine steel particles that settle onto a different type of metal, then those can cause pitting in the machine. Human health is something that we're even more interested in than the health of buildings, because things are replaceable, but your health, once it's gone, it's usually gone forever. So particulates like PM 2.5 and PM 10, those very small particles that can get into the lungs, one of the reasons why we're so anxious to avoid that is that it can get into the deepest recesses of the lungs and cause a chronic inflammation. And over time, even if the particle itself is inert, the inflammation can develop into a cancer. And there's a material called asbestos that for a long time was used as an insulation in buildings. Sometimes not here, thankfully the universities knew enough, but in older buildings sometimes asbestos was even in floor tiles. And that's a material where asbestos itself isn't necessarily toxic, but it's a very, very small, thin particle that would get deeply embedded in the lungs, and the lung would be chronically irritated from that, and over time it's the irritation that would cause into turn into cancer. So particles can be dangerous into the lungs, and so can aerosols. An aerosol is a very, very fine droplet of water or some other liquid. It's a particle that's so small that it's a liquid, but it's suspended in the air. And of course, the smaller the particle, the more dangerous it is, because large particles get caught early in the respiratory system and then they can be coughed out again. But the smaller the particle, the more deeply embedded it gets in the lung, and the less likely it is that you can get it out through a cough. Some of the ways that we can measure air pollution, one of the ways is called a high volume sampler. And this is for measuring particles. And you can think of it as sort of a vacuum bag. It's basically sucking a certain volume of air through a filter, and on that filter they would weigh it before they start to sample the air, and then they would weigh the filter later to find out how much mass has accumulated on it. And so it's very similar. You had a homework example one time where we were putting water through a membrane disc, and they measured the mass of the membrane before and after filtering it, a certain volume of water through it. And this is similar to that, where you would do a weigh before and after, and then depending on how much air went through there, you can know the mass per volume. Concentration would be micrograms per cubic meter. So if you know how many micrograms, the mass of that filter increased, and if you put, for example, 1,000 cubic meters of air through the sampler, then that would allow you to calculate the volume. 20,000 happens to be a pretty standard volume that's used in this sort of analysis.
You vacuum the air constantly?
You do. You would, underneath the vacuum, underneath the filter, you'd be sucking the air in. You can use a blower to force it through the other direction. But at the end, the filter will look dirty if you're in a polluted area, and that can be a way of sampling how polluted the air is. Another way to do this, you can get, the disadvantage of a method like this is that it takes time, because if it's a 24-hour measurement, 24 hours that you're sucking the air through the filter, then it takes you time to know essentially what the conditions are. And those can change very quickly through a day. And so a nephelometer is a way of getting an instantaneous measurement, and that's just by measuring the clarity of the air. And so if you shine a light through a certain length of air and you know how much of the intensity of the light decreases, you can back calculate from that what's the particulate concentration. And for example, one of the places that's kind of famous these days for having really poor air quality is Beijing, China. And the government of China is now starting to release statistics about what the air quality is in Beijing, but for a lot of years, the only way people knew what the actual air quality was by looking at the measurements from other embassies in Beijing, because the Chinese government itself wasn't releasing any air quality data. So people would have to look at the embassy releases to know what was the air quality. And they were using a nephelometer because they wanted instantaneous measurements of how the air quality was changing through the day. Not all air pollution comes from humans, though. Some of it's just naturally occurring. And so here's a list of some of the natural sources. If you think about sometimes in the spring or in the fall, your allergies may act up, may get a runny nose or start coughing. And that can be because of pollen grains. When the flowers start to bloom, it releases very small particles. It can be volcanic emissions. And there was a big case maybe about 6 or 7 years ago now where there was a volcanic eruption in Iceland. And it delayed a lot of air traffic in and out of Europe because the visibility was reduced and people were worried that it might interfere with the engine ability. Salt spray can be a source of pollutant where, salt, of course, encourages corrosion of metals. And so if you're living close to a coastal area, you can experience more corrosion because of just the salt that gets into the air as the waves are crashing over rocks. So these are some of the particle sources, but there can even be gaseous sources of pollution that's naturally occurring. And as hard as it is to believe, sometimes it's from trees causing air pollution. And let me show you this picture. It's a famous mountain range in the United States called the Smoky Mountains. And they're called the Smoky Mountains because it always seems very hazy in this area. There's no factories, there are very few cars, there's not very many cities, and so the hazy air pollution that's always in this area is just because the certain kind of pine trees that they have in this region are emitting hydrocarbons. And so that is one source of naturally occurring air pollution that it sort of causes a photochemical smog in the same way that vehicle emissions does. Methane can be emitted from animals. Nitrogen oxides can form from emissions from volcanoes. And so most of the time pollution is our fault, but sometimes it's a naturally occurring phenomenon. Here's a picture of a volcanic eruption in the Philippines back in 1991. And this was such a significant eruption that they actually measured on the Earth's surface, the global temperatures went down by ½ degree. That doesn't seem like a lot, but it has a huge impact. That actually a ½ degree is enough shading of the sun that it had an effect on crop productivity. There was dust settling over, thousands of miles away. The volcanic eruption dust was settling, and it was kind of a really interesting study in what naturally occurring pollution can do. Some people have suggested that in order to counteract global warming, some people are saying that we should release particles into the atmosphere to do shading, and they always refer to Mount Pinatubo in the Philippines as an example of how that would work. If global warming is bad, then we can do global cooling by putting particles into the upper atmosphere. That's called geoengineering, and it's almost certainly a terrible idea. Huh? Right, yeah, it could be bad. They say that the shielding of the sun's rays, if you have little particles up in the upper atmosphere, it could screen out some of the sunshine and then it would cool off the Earth. But there would probably be some side effect we haven't thought of. Here's a word that is in your homework assignment, anthropogenic. That means man-made. And so some of the pollution is naturally occurring, but most pollution is man-made, and it comes from burning things. like combustion of wood, natural gas, coal, anything that we're doing to try and harness energy that's not a renewable resource like solar, can cause pollutants like carbon dioxide, sulfur that can form sulfuric acid, particulates, hydrocarbons. Vehicle emissions are a pretty common source of air pollution, and single passenger cars have a disproportionate share of pollution because single passenger cars are more difficult to track the emissions of than larger vehicles like a train or a boat or an airplane. Usually they're more carefully maintained, those larger, more expensive pieces of transportation equipment, than cars that in some cities they have emissions checks and in most cities they don't. Sometimes before you register your car, they'll actually put a sensor in the tailpipe and measure what is the concentration of nitrogen oxide that's coming out, carbon monoxide, and so on. But most cities that don't suffer from really terrible short-term air pollution don't bother with the monitoring, and so vehicle emissions aren't regulated as much as they ought to be. There's a couple of different ways that the health effects can accumulate on the body. And these are terms that you need to be acquainted with because whether it's air pollution or pollution that comes to us from our water or from food, these effects can come into play. Now, threshold is the idea that sometimes you can have a little bit of exposure to a pollutant and it won't harm you at all. And so it's the idea that you have to achieve some total amount inside you before you start to notice any side effects. Total body burden means that you can get exposed to some pollutants from multiple different routes. And so one example of that is chlorine. When you drink water that's been disinfected, chlorine is often used as a disinfectant that's persistent in the water. And even when you're pouring the water from the tap and drinking it, you're getting a little bit of chlorine exposure into your body. Well, you can also get chlorine exposure through the air if you have a cleaner that's cleaning the floors off with bleach, which sometimes they use to whiten the tiles. The chlorine can be gaseous, and so it's coming in through your lungs. You can get some chlorine exposure to your eyes. Sometimes the pollutants can sorb through your skin. And so there's lots of different routes that a chemical can get into your body just besides your mouth. Synergism is a concept that sometimes two pollutants that are in your body at the same time can have a bigger effect than any one of them individually. And an example of synergistic effects is that people who are miners, they go underground to mine coal, for example. There's a little bit of risk of, well, not a little bit, there's a risk that the coal dust underground gets into their lungs and causes an irritation. And so there's a certain effect from that. Let's say it gives them a 10% chance of cancer. And then smoking can cause cancer. Maybe there's a 25% chance of cancer from smoking. But if you smoke and you're a miner underground, those two effects together would cause maybe an 85% chance of cancer, where the sum of the parts is greater than each part individually. And so that's the meaning of synergism, that there is a combined effect that's unusually large. And finally, time versus dosage is talking about how you can either have a short-term exposure to a high concentration or a long-term exposure to a lower concentration, but you can suffer the same effects. It's not just a function of how high the concentration is, but also the amount of time that you're exposed to a pollutant. This shows that effect, that, for example, if we are talking about carbon monoxide, and I referred to this in the last lecture, that sometimes you hear in the news about like a family just in the morning their water heater malfunctioned and everyone's died because of exposure to carbon monoxide. This is showing over time what different concentrations of carbon monoxide will do. For example, this really high concentration of 500 milligrams per cubic meter in the air. If the exposure time is 1 hour, then it will cause a headache. But if you're exposed to that same concentration for 10 hours, it's getting you very close to the threshold that causes death in some people. And so it's partly concentration and partly exposure time that causes the real effects there. All right, now today for the rest of our class period, we're talking about how we can model indoor air quality, like calculations we can do that will tell us what's the concentration of pollution indoors. And it's really important because we spend a lot of time inside. You know, here in the UAE, especially during the summer months, think about what percentage of your time do you spend either in a building or in a vehicle. Like 99% if you're lucky, right? If you're unlucky, you're spending time outside during the summer. So that's why it's important for us to focus on indoor air quality, because we spend so much time indoors. So we can get carbon monoxide from furnaces, gas stoves as they're burning gas, that can give off nitrogen oxides. There's a radioactive pollutant in some places called radon. I don't think it's much of an issue here, but depending on the geology of where you live, this radioactive gas can just seep up from the foundation. Sometimes the adhesives that are used in buildings to glue down floor tiles or carpet, or the paint that goes onto walls can contribute to volatile organic compounds. That's what VOC stands for, is volatile organic compounds. And unfortunately, cigarette smoke is a big source of indoor air pollution. Even in places where indoor smoking is illegal, somehow it still seems to be happening once in a while, like every day between classes in every restroom in this campus. So here's an illustration of radon, what I was talking about, where there's a radioactive decay of gases that get into people's basement, and in a lot of places, before you sell a house, they'll test the radon concentration to see whether it's dangerous. And if they're detecting a lot of this radioactive gas, then they'll have to spend some money to seal up the foundation to try and prevent the gases from getting into the building. And this, I don't know, this is just an illustration of what I want to put on when I go into the restrooms here when people are smoking, because it's so terrible. All right, here is indoor air quality model. It's basically the same idea that we've been doing from the beginning of the course, where we're looking at accumulation. So accumulation of mass is the flow in minus the flow out plus production minus consumption. All right, so what we're looking at is the accumulation. So think about this room. If we sealed off all of the air vents so that there was no flow of air in or out, and we lit a fire, we could keep track of the accumulation of mass of pollution in the room over time as a function of production. That's what lighting a fire in this room would be, a production reaction. Consumption would be if we had a filter in here that was somehow taking the particulates out of the air. Like if it was filtering it through they have fabric filters or bag filters that can remove particles. And so production and consumption are both reactions that are occurring inside of a room. Flow in and flow out takes a look at the rate that pollutants are either coming into a room or going out. Sometimes it's a problem when they have the air intakes of a building right next to a loading dock. That's really bad architecture. And in fact, there's a building on campus at Marshall University where I normally work, where they have the air intakes for the building next to a loading dock. And the problem with that is, you know, a truck will show up to deliver some equipment, and the driver doesn't want to turn off the truck, and so the driver's just leaving the car idling. And it's sucking the air for the building close to where that exhaust is, and so just out of the blue, you're in your office, and all of a sudden it starts to smell like diesel fumes. And that's because the flow into the room may be from a contaminated source. So in our air quality model, we can keep track of the mass of each of these constituents by Q times C sub A, which is our concentration in. This is going to be, if we multiply flow rate by concentration, that will be mass per time. Each one of these terms is mass per time. The emission rate would be mass per time, and here V with a strike through it, that means volume, and it's meant to distinguish, sometimes V is used for velocity as well. And so if you ever see a V with a strike through it, that is intended to mean volume. So we're going to apply this mass balance model to some indoor example, and we can keep track of the decay of pollutants. There's a table in your text that says different types of chemicals and how quickly they break down. Maybe they're sorbing onto the surface and that's why they're decaying. Sometimes it's a radioactive decay in the case of radon. But you can see some of these have a rate constant that explains how quickly the concentration is just naturally going down in the air. And so this model, what it's showing is the flow in and the flow out of chemical constituents, and there's maybe a source emitting pollution and then a sink, which means something that the pollution is sorbing onto over time. Here's the equation that we can use to calculate a steady state concentration. Steady state means when the concentration has reached equilibrium and isn't changing anymore. And so if we lit a fire in this room right now, there is some ventilation coming in, there's some ventilation going out under the door jamb. But if we lit a fire, the concentration of carbon monoxide would go up. It would start from 0 and it would go up, but then it would reach an equilibrium where if the fire is burning at the same rate and the gases are flushing the pollution out at the same rate, eventually it would settle on some concentration C. C sub A is the concentration of the pollution in the air that we're flushing the room with. And so if there's pollution in the air that is supposed to be flushing out whatever gases are in a room, then that's what you would set for C sub A. Sometimes we have pollutants that don't decay and the K value is 0, and that simplifies the equilibrium concentration a little bit. We can use this reaction when K equals 0. So here is what we're going to work on to try and get a feel for these air quality calculations. We have a room where we know the dimensions. The dimensions of a certain room are 4 meters by 8 meters by 4 meters. This is a basement, which is the locations that are most prone to exposure from that radioactive gas radon. There is, based on our estimations, 38 micrograms per second of radon seeping in through the foundation, entering the room. We're going to consider that as an emission rate E, 38 micrograms per second. There happens to be a little bit of radon in the ventilation air, so C sub A is where we're going to put the concentration of the ventilation air. And then we know that the air exchange rate, or the ventilation rate, is 100 liters per minute. And so that's the Q. The Q that it's talking about here is what rate the air is flowing in and out of the room. So there's two things we're going to consider in this example. First of all, calculate the concentration of radon in the basement when the conditions do reach steady state. And then the second part, we're going to find out if we want the concentration to be lower than this concentration we calculate for part A, would we have to increase or decrease the ventilation rate to achieve this limit, 500 micrograms per cubic meter? All right, so the equation you need is here. Everyone's got a copy of the in-class exercise, right? And then part C on your paper, not shown on the screen there, but part C, I'm asking you, what's the air exchange rate? We'll talk about that when we get to it. Let's just focus on part A and B for now. Okay, so part A, we want to find out what's the concentration of this pollutant in the room. Yeah, it should be 19,691 approximately, depending on how you round it off and so on. 19672? Okay, fine. I want to point something out, is the different pieces of this formula and what it means. Okay, when we substitute into the equation Q times C sub A, that's the flow of the pollutant into the room. And so how much, it maybe seems like there's more pollution coming into the room than the emission rate, because if you just look at the numbers, 38 versus 85, but that's not true, because the air coming into the room is much cleaner than the air coming out. The air coming out is 19,000, and the air coming in has a concentration of 38. No, 85. 85. So 85 is less than 19,000, so the air coming in is relatively clean. And so on a mass basis, how much mass of radon is coming into the room every second? It's 0.14 micrograms per second of radon coming in versus 38 micrograms per second of radon coming in. So the majority of this concentration that we're seeing is because of the emission. The emission is much greater than the inflow of the pollutant here. All right? Now look at the denominator. What you want is you want a big denominator, because we're talking about a pollutant. We want the air concentration of the pollutant to be as low as possible. And so how is most of the removal of the pollutant achieved? Is it through flushing or decay? And so if we look, there's 0.001667 cubic meters per second of flushing. The equivalent of that, due to the decay, if you multiply the K value by the volume, you can see that decay is a much smaller explanation. The volume equivalent of the decay is 0.00027 cubic meters per second when we multiply those two together. So most of the pollution is coming into the room through emission, and most of it's leaving due to flushing rather than due to decay. All right, so any questions about Part A? Okay, Part B, what it's asking is, what do we have to do? We should change the Q to get the concentration in the room below 500. Right now, it's 19,000. That's too high. That's not good. So we want to increase the Q, because if we're increasing the flushing, that'll bring the concentration lower. So solve for what Q is required to have C equal to 500. And we already know Ca, we know E, we know V. Okay, so the only unknown will be the flow rate Q. Maybe you can put it into your calculator directly and solve for the unknown. I did like the algebra rearranging until I isolated the variable. Solve for Q. Okay, so Part B, here you can see I went through the lengthy process of trying to isolate Q in that equation. There it is. You can solve for the flow rate. Let me ask you, why do we have to have a higher flow rate to have a lower concentration of pollution in the room? Let's think about it. The flow rate into the room used to be 100, right? 100 liters per minute. And we had a really high pollution concentration. It was 19,000. What this is saying is, if you want the pollution to be lower, give it more fresh air. I mean, that makes sense. When we come into this room and it doesn't smell good, right? Like after the other class, what do? We open the windows, right? We open the windows and we're increasing the rate of flushing. So this is the same thing. It's saying if the air pollution is too high, you have to increase the rate that the clean air is coming into the room. So that's why we have 74 liters per minute instead of 100, is because bring it more clean air and then the pollution will go down. Okay, Part C. It's asking about the air changes per hour. Let me just show you that, and I think as soon as you see it, it'll make sense to you. If our room is 128 cubic meters, and we're going to be having our air come in at 5.474 cubic meters per minute. So here I've just changed it from the liters per minute to cubic meters per minute. Then that means that it's 328 cubic meters per hour that we're ventilating into the room. Air changes per hour just tells you how many times per hour are you replacing the volume that's in the room. And so you can see I've got Q divided by V. And that will give you air changes per hour. So every hour I'm replacing the air in the room 2.5 times when I have that high flow rate. So it's kind of like you're giving it an entirely new air system, 2.5 times per hour. You have a question on your homework that asks us about ACH, air changes per hour. And there you have it. It's just the flow rate divided by the volume. Any last questions? Please put your in-class exercise on the chair. And oh yeah, we've got a field trip tomorrow, right? So we've got class until 1, and then is it 2:15 that we're supposed to meet for the... I'll be there at 2. And I think the cars leave at 2:10, 2:15. And we're going to go see a wastewater treatment plant. You're going to kick your vacation off with a bang. It'll be great. All right, see you tomorrow.